Hello my dear students, in this lecture we are going to see one question on infinitely long fin. The question is very interesting. The question is two long rods of same diameter. Now here they have given two rods, right? Two long rods of same diameter, right? One made of brass, one is made from the brass having thermal conductivity. Let us say the brass I am assuming as 1. Here for brass I will assume as 1, right? Therefore thermal conductivity of brass K1 will be equal to 85 watt per meter Kelvin. It is given, right? And other made of copper. Now let us say for copper I will assume 2, right? For copper I will assume 2. Therefore thermal conductivity of copper is given K2, which is nothing but 375 watt per meter Kelvin. Therefore thermal conductivity of copper is equal to 375 watt per meter Kelvin. Then now two long rods of same diameter, one made of brass and other made of copper, have one of their ends inserted into a furnace. Now for both rods, one end is inserted into the furnace. Let us say here there is a furnace, and one end of both, let us say this is a brass rod, here this is a brass rod, right? And here there is a copper rod, and both will be having same diameter. Here the cross section is circular. For both the cross section is circular of same diameter. Now let us say the top one is brass rod. Therefore for brass we have written 1, and the bottom is copper rod. For copper we have written 2, right? Now for both rods, one end is in furnace, therefore temperature at this end will be same for both. That is T naught. That is T naught, base wall temperature. T naught will be same for both, right? Then both rods are exposed to the same environment. The meaning of this statement is the surrounding fluid is same, means convective heat transfer coefficient and surrounding fluid temperature for both rods is same. Here edge and surrounding fluid temperature will be same, right? At a section 10.5 centimeter away from the furnace end, the temperature of brass rod is 120 degrees Celsius. Now here distance is given. Let us say for brass we have written 1. Therefore at a distance of 10.5 centimeter away from the furnace end, the temperature in the brass rod is 120 degrees Celsius. Let us say here at distance, I am assuming distance as a x or x1, the temperature will be T1, right? Temperature will be T1, right? And x1 is given for brass. Therefore, if x1 is equal to 10.5 centimeter, the temperature T1 in the brass rod will be equal to 120 degrees Celsius. Then, at what distance from the furnace end the same temperature would be reached in the copper rod? Now they are asking at what distance, let us say x2, at what distance in the copper rod the same temperature is reached. Means here also the temperature is T1 only. Therefore, for here we have to find x2 if temperature in the copper rod will be equal to same as that of brass rod, that is 120 degrees Celsius, right? Now it is very simple question, my dear students. Now let us quickly summarize this question. Now see, there is a one brass rod and there is one copper rod. Now both rods are infinitely long, very long rods, right? And one end of the both rod is subjected to same environment. Therefore, this base wall temperature will be same for both copper as well as brass rod, right? And my dear students, the surrounding environment is also same. That is means convective heat transfer coefficient EH and T infinity. That is surrounding fluid temperature is same for both rods. And in case of brass, here first number is brass. Here this is the brass, and second is copper. Here for brass, at distance of 10.5 centimeter away from the furnace, the temperature is 120 degrees Celsius. Now for copper, at what distance away from furnace end, the same temperature will be there, that is 120 degrees Celsius. Right. Now my dear students, as here the long rods are given, for long rods we have seen temperature distribution. That is this temperature at any location, let us say here we have written temperature T1 and temperature T2. Temperature at any location minus surrounding temperature divided by base wall temperature minus surrounding temperature is equal to e to the power minus mx, right? This formula we have seen. And my dear student, this temperature, that is T1 T2 for both rods is same, surrounding temperature is same, base wall temperature is same, means for both rods this factor is same. Therefore let us erase this question so that we will get sufficient space, right? Now let us understand what they are mentioning here. Now, don't erase the given data, right? Now, here this ratio T minus T infinity divided by T naught minus T infinity is same for both. Therefore, I can say e to the power minus mx will be same for both. Same for both. Therefore, this minus mx will be same for both. Right? That means minus mx of brass will be equal to minus mx of copper. Therefore, minus minus will get cancelled. Therefore, we can say mx product of brass is equal to mx product of copper. This will be the condition. Right? Now, what is this m? Let us find this m first. Right? Now, my dear students, here so we have derived the case mx product of brass is equal to mx product of copper. Right? Here I will write mx product of brass will be equal to mx product of copper. And this em is nothing but in terms of fin, it is nothing but under root of hp divided by ka. Right? It is hp divided by ka. H is convectivity transfer coefficient, which is the same in both cases. P is perimeter. Now, for both cases, diameter is same, therefore perimeter is also same. A is thermal conductivity. Now here thermal conductivity is different for both cases. And A is cross-sectional area. Now in both cases, diameter is same, therefore area is also same. Therefore, can I say here H, P and area is same. Therefore, this em is inversely proportional to under root of 1 upon k. Right? It is inversely proportional to under root of 1 upon k. Right? Therefore, my dear students, the ratio this em of copper divided by em of brass, right, will be equal to under root of k of brass divided by k of copper. This is how we can understand, right? So, my dear students, let us find this ratio, right? Therefore, m of copper divided by m of brass. Instead of this, if I find reverse, m of brass divided by m of copper is equal to, it will become under root of k of copper divided by k of brass, right? So let us put the values. We have copper and brass values, which is equal to under root of thermal conductivity of copper is given 375, thermal conductivity of brass is given 85, right? If I calculate this, I think the answer will be 2.1. Answer will be 2.1. So my dear students, here we got the ratio. Here, just a minute, I will write this ratio. Right. Now here we got the ratio, that is em of brass divided by em of copper is equal to 2.1. Now once you got this ratio, right, now it is simple to find x, right? So my dear students, let us use this relation, that is m into x product is same. Therefore here we can say m of brass into m x of brass is equal to m of copper into x of copper, right? We have to find x of copper. Therefore, this x of copper, distance of copper for same temperature will be equal to m of brass divided by m of copper into x of brass, right? Therefore, x of copper will be equal to this ratio. Just now we have calculated 2.1, and x of copper, the location of copper is x1, which is 10.5, right? So let us simplify. I will get the answer is 22.05 centimeter. Therefore, my dear students, in brass, if temperature is equal to 120 degrees Celsius at 10.5 centimeter away from the furnace end, then the same 120 temperature in copper will be at distance 22.05 centimeter. That means the component having higher thermal conductivity will get lesser drop in temperature, right? Will get lesser drop in temperature, definitely, because in copper thermal conductivity is more, therefore heat transfer is more. That's why, as heat transfer is more, that's why the same temperature in case of brass will be nearer as compared to copper, right? Now my dear students, in next lecture we will see one more numerical on this topic.